Hi, Amanda. Sorry, I was a bit late. So.
Oh, you're good.
Hi, Yinon.
Hi, hello.
How are you?
I'm good, thanks. How are you?
Good.
So is this the first talk of the series?
Yes.
Okay. I'll start.
Sounds good.
You can share your screen if you want.
Sure, yeah.
Cool.
And the talk should be 50 minutes, an hour?
Yeah, sure. Anywhere in between 50
Okay.
minutes and an hour is good.
Okay. Great.
We usually start a couple minutes late.
So are you at UBC now?
Yeah, I'm here at Vancouver. I'll be here for 1 more year. And I'm going back to Israel, to Tel Aviv.
It's great. It's such a beautiful campus. I visited UBC a few years ago, and it was, in the summertime it was so nice.
Mm-hmm. Yeah, it's really nice. Yeah, the can see the mountains and the ocean, and yeah, it's really nice. And they are building buildings all the time, which is not great, but I guess it's like that everywhere. Yeah.
Yeah, it's like that in Austin for sure.
Yeah. Yeah, same thing in Tel Aviv as well. You always get less and less grass every year on campus.
Should we get started, Louis? Do you think this is a good time?
Yeah, sorry, sounds good to me. So you want to introduce?
Yeah. So we'll get started. Thank you for coming, everyone. This is the first talk in a series of talks on factors of IID. So today we have Yinon Spinka speaking on entropy-efficient finitary codings.
Great, thanks a lot. It's a pleasure to be here and to open this mini series. So, so first of all, if at any point something's unclear, or you want me to clarify something, or even push me in a different direction, I'd be happy to answer any questions. So feel free to ask. Everything I'm going to talk about today is based on joint work with Tom Meyerovitch, who's at Ben Gurion University in Israel. So let me begin just by giving the basic definitions. So I'll be talking about codings or factors between processes on ZD, so indexed by ZD. actually everything I say is already pretty much everything is already already in the one-dimensional case. So if you want, you can just have in mind regular Z processes. That's not, you won't lose too much. I'll talk about things in this in higher dimensions as well in certain places. And actually, I'll also say something about even a more general setting. I'll get to that in a minute, but I won't really focus on that in the talk. I'll just mention that shortly. So the processes here are always assumed to be translation invariant in distribution. I'll have mostly two processes, X and Y. The state spaces here, A and B. For now, I'll assume that they're countable. If you want, you can even have in mind finite valued, but at certain places, I will want to allow more general things, at least for the process, the top process. Right? We have a factor from one process to another. So in certain situations, I will want a more a larger state space to be able to talk about continuous random variables and so forth. But for now, you can just imagine these are countable. Okay, so let's begin. A coding from the process y to x is a measurable function from the space of realizations of y to that of x, such that phi of y equals x, and phi is translation equivariant, which means it commutes with translation. So if we apply phi to the input y and then translate the output, what we get is the same as if we would reverse the operations. If we first translate the input, then apply phi, we would get the same thing. So that's kind of like saying that phi isn't aware of the names of the vertices. So everything kind of looks the same everywhere. And this equality here in the first part, I'll kind of switch between, depending on context, this might be equality in distribution or equality almost everywhere, almost surely. And I hope that shouldn't be too confusing. Anyways, if you have equality in distribution, there's always a probability space where you can make this equality almost surely. So if I'll jump between those two viewpoints. Okay, so that's a factor or a coding. And to define a finitary factor, I need to introduce this coding radius. So this is a random variable, capital R. It's the minimal R, such that the output at the origin is determined by the input variables on a ball of radius R. And the norm here, it's not going to be important for anything I say, so you can choose whatever norm you want. I'll talk about balls. You can think about boxes if that's more convenient. It doesn't really matter. So okay, and the coding is finitary if this random variable is finite almost surely. So what this means is another way to think about finitary factors is so first of all. Okay, so to determine the output at a specific point, which for some reason I drew as a face here, not as a vertex, but anyways, that's not so important. The output at a certain point is determined by a big ball in the input, but that ball it doesn't have a predetermined size, and doesn't even have a bounded size a priori. It's random depending on the input. So you can imagine that you have an algorithm to determine the output at a vertex. So the algorithm reveals the value of y at the corresponding vertex, looks at it, decides, okay, do I know the output or not? Maybe I do, and the algorithm stops and outputs a value. Maybe it doesn't, and it decides to reveal a larger neighborhood in the input. Then it looks at the values of the input on that larger neighborhood, again, does some computations, whatever computation, decides does it know the output or not. If it does, great, and it stops. If not, it increases the neighborhood and continues. And what it means to be finitary is that this algorithm is guaranteed to eventually stop at some finite time and say, okay, I know the output, this is the output. And what that means is that at that point in time, you didn't look, the algorithm didn't reveal any values of the input outside this ball, and And so it's determined just by the input on that ball. And different vertices are determined by the exact same algorithm. That's because of this translation equivariance. But because the algorithm sees different inputs, the output might be different, and the size of the ball, which determines the output, might be different, and so forth. So at every point we have a random variable which kind of corresponds to the coding radius, but they all have the same distribution, and therefore to define the notion of finitary, it's enough that's why I just looked at the value of the output at the origin. Okay, so this is the notion of a finitary coding or finitary factor. Okay, so I hope that's clear. If not, again, please feel free to ask questions at any point. Okay, so as I said, you can have in mind Z if you want. I'll talk about ZD very often. This is a very natural generalization. And in ergodic theory, it's also natural to generalize this to a countable group. So you have processes which are indexed by the elements of a group, and they're invariant to the group action. And everything here generalizes to that situation, except perhaps the notion of a coding radius, which isn't always. I mean, this relies on some metric, and then that you might not always have a natural metric in a countable group, but these two conditions together really, I won't talk about the coding radius at all in this talk, and it was only in order to define the notion of finitary, and then has a very simple definition even without a metric. It just means that almost surely there's a finite set of input random variables which determines the output. So it doesn't have to be balls, it just needs to be that you look at more and more of the input, and at some point you know the output. So that's a natural generalization in ergodic theory. I'm more of a probabilist, actually. I actually don't know too much ergodic theory, and for me, the natural generalization of ZD is actually a transitive graph, locally finite graph. So ZD you can also think of as a graph where, here's the graph, right? So two sites are adjacent if their distance is exactly 1. And we can replace ZD by an arbitrary transitive graph, and then everything here also generalizes to that situation. Transitive graphs are almost a generalization of countable groups, except really it's only finitely generated countable groups. And then when you look at the Cayley graph, that gives you a locally finite transitive graph. But I just like to say, even already on ZD, there is this additional nuance, which again I won't talk about here, but I just want to mention this. Even on ZD, you can replace the translation equivariance with equivariance to all isometries of ZD, or when you think about it as a graph, all automorphisms of the graph. And that gives slightly different notions. Okay, so let me also tell you what the more general setting which captures both of these, which generalizes both of the settings I just described. And again, I'm just going to mention this, and then I won't talk about this during the talk, but just for you to have in mind that there is a more general setting which captures both of those, both the group view and the graph view. So we have a countable set V, which is kind of like the set of vertices. We have a group of permutations of V, which is kind of like the automorphism group of the graph. Then we'll be talking about gamma invariant processes indexed by this countable set and gamma equivariant codings. And most of the results that I described, they work in this framework under some assumptions on this group, which we called, for lack of a better name, a nice permutation group. So the assumptions are that gamma acts transitively on V. The stabilizers of gamma in V, so if you take an element of V and you look at the stabilizer of gamma, of that element, that has finite orbits. That's kind of analogous to the graph being locally finite. We want gamma to be unimodular. And we have this extra technical condition, which is kind of just to rule out some weird situations. We want IID processes to be aperiodic. That doesn't follow from these previous assumptions. And for a lot of the results I'll mention as well, we also need amenability. Okay, so that's just some general framework. Maybe if you haven't seen this before, it's nice to have in mind that there is something that generalizes both those types of scenarios. But again, I'm just going to go back and talk about ZT from now on. Okay. So perhaps the first thing to discuss, which really is more of a background here, is what happens for IID processes. So in this, here X and Y were just any processes. Let's restrict ourselves for a minute to IID processes. And talk about factors and finitary factors between IID processes. There's this very nice example of Mishalkin back from 1559, which, okay, I'll describe it perhaps differently than how it was originally presented. So one IID process, which I'll call the input, has the state spaces of size 5. There's 5 possibilities at every site. And instead of calling them just 1, 2, 3, 4, 5, it's going to be convenient to give them different names using these symbols. So one of the states is a circle, one of them is square, circle, circle, square, circle, square, and so forth. And the probabilities aren't all 1/5, 1/5, but 1/2 for the circle and 1/8 for the others. So that's the input IID process. And here's a realization at the top of this process. And before I tell you what the output process is, let me just describe what the coding is, and we'll get to the output in a moment. So the coding can be thought of as, when we think about the process using these symbols, we just apply a strong wind just to the objects at height 3. Okay, so we have the bottom level 1, 2, and 3, and we're only going to apply it to things at the top level, and we're going to push them to the left. Okay, and as they move to the left, they're going to start falling down into the empty holes. Some of them are going to fall, some of them are going to continue, and then something's going to fall and continue, and so forth. And you can convince yourself pretty easily that because at every site, there's either a hole, a vacancy, or a surplus with probability half, independently, IID, that eventually every vacancy will be filled by a surplus. So this one's going to go to here. This one comes here, and in the procedure I just showed, this is going to continue somewhere else. But every vacancy will eventually be filled by a surplus, and every surplus will eventually fill a vacancy. So they're going to be matched exactly to each other at some point in time. And what that means is that we can that if I decide that the output is it's a well-defined output to say that I take the 2 symbols that eventually stabilized and ended up at the bottom two levels. Okay, so that's my output. And it's not hard to convince yourself that, well, obviously there's these 4 possible outputs. It's not hard to convince yourself that each of the outputs is equally likely, and moreover that it's independent at different sites. So in other words, the output process is exactly IID, uniform on 4 symbols. And moreover, actually, this whole entire coding is invertible. So if you see the output process, you can invert everything and figure out what the input was. So actually, this is an example. Okay, and one more property that we should note: if you want to figure out what the output is at a vertex at a certain site, for example, in this situation, if we want to figure out, here's the input, and we want to figure out what the output is here, what do we have to do? We just have to start looking to the right until we see 1 surplus more than vacancies in total, because if we see a vacancy, now we know that the next surplus is going to fill that vacancy. And if we see another vacancy, we know that the next surplus is going to fill that vacancy. But once we see one surplus more than a vacancy, we know that that's what's going to fill that specific vacancy, and then we know the output. So in this specific for this specific input, to determine the output at this location, it's enough just to see that just to see the input on this window. It doesn't matter what happened anywhere else. We know for certain that the output is going to be circle square. Okay, so that also shows that this is finitary, and also the inverse is finitary. So actually, this is an example of a finitary isomorphism between these two IID processes.
I'm sorry. How do you know that there's going to be that surplus within a radius r?
Okay, so the r is not fixed. It's random, and I can even tell you in this case exactly what its distribution is. It's just the distribution of a simple random walk excursion. You start a simple random walk from height 1, and you wait until it hits height 0, because you're waiting for one surplus more than a vacancy. So it's just a simple random walk, and that simple random walk is recurrent, so it's almost surely going to hit 0. So it's almost surely a finite random variable, and you can even figure out its distribution using random walks and things like that. Does that make sense?
But right. So, but basically, almost surely finite is good enough. You're not actually requiring finite.
Right. Almost surely finite, and it's almost surely finite, and moreover, I'll just repeat this just to make sure it's clear. This random variable depends on the input. Okay, it's a function of the input. It's actually a stopping time of the input. You see more and more of the input. At some point, as a function of the input, you decide to stop, and it's an almost surely finite stopping time. Yeah.
Okay, thanks.
And then just continuing along this line, if there is an integer k so that this radius r was almost surely at most k, then this coding would be almost everywhere continuous?
Okay, so okay, I actually maybe perhaps did want to say something about this, so thank you for the question. This has to do with the state spaces, whether they're discrete or not. So let me first answer the question when they're discrete. When they're discrete, or let me say it more generally, when they're in general, if the coding radius is almost surely bounded, we call this a block factor. Okay, and the question of when block factors are continuous maps, that's true when the state space is discrete. But in general, and as I said, I will want to think about more general things, it doesn't have to be continuous. Okay, but it is a function of finitely many of the inputs, but a measurable function, which perhaps is not continuous.
When
Right,
you say continuous, are you talking about like the product topology on X and Y?
Yeah, X, yeah, on this space here, yes, product topology, yeah.
Well, it's also the other way around, that you can have something that is continuous but is not finite.
That's right. So in the setting of discrete state spaces, there's really okay, so this is the definition of finitary, but when you move into a more general state spaces, there's really two ways to generalize the notion of finitary. One of them is to ask that the map is almost everywhere continuous. That's one generalization, and the other generalization is to ask that more in the as it's written here, that you have a stopping time which determines things. That's more of a measurable definition, which has nothing to do with topology. And in general, these two definitions are not comparable. But in the case that all the state spaces are discrete, they exactly coincide. Yeah. So that's a bit of a technicality, which, okay, it will be relevant at some point, but I'm kind of not going to go into that. I mean, if you have any questions, I'd be happy to answer, but if you don't, I'll just hide that under the rug. Okay, so let me tell you a bit about, let's see the time, okay. some history about codings between IID processes. So for Z processes, so I'll talk about just for the history about Z processes, about processes over a countable group, factors, isomorphisms, finitary factors, finitary isomorphisms. So the classical thing is Z processes, which are non-finitary. So we have Sinai's factor theorem, and we have Ornstein's isomorphism theorem. So, I believe, I guess everyone knows these results, right? So, so if X has entropy less or equal than Y, then Sinai proves that there's a factor from Y to X, and if they have the same entropy, Ornstein proves that that there's an isomorphism between the two. Of course, for Z processes, entropy is preserved by factors. Over a countable group, in general, we don't know that entropy is preserved, and I'm not going to be worried about that direction too much in this talk. I'll just assume that the entropy of X is at most the entropy of Y, or for isomorphisms that they're equal, in fact. And Ornstein and Weiss proved that when the entropies are equal, there is an isomorphism over an amenable group. Lewis showed that this is true over general groups, with the small caveat that the IID process can't be, random variables which are Bernoulli, 0, 1 valued. Can't have just 2 symbols, you need at least 3 symbols. There's some technical reasons for that, and then very recently Seward filled in that gap. Okay, so over countable groups, we know that we always have isomorphisms between IID processes of equal entropy. Okay, so what happens in the finitary case? So over Z processes, this was first done by Yinon Smordinsky in '77. They first came out with a paper where they showed a finitary factor when X has entropy strictly less than Y. They did this only for finite valued IID processes. Then a couple years later, they did an isomorphism for finite valued processes. Petit extended this to the infinite entropy case, countable valued still. Yeah, everything here is countable valued IID. And as far as we could tell, the case of finite entropy but countable state space was not addressed previously, and it follows from our results. So that fills in that gap. And then over a countable group, what is known? So again, in this paper of Seward that I mentioned, we have finitary isomorphism in the finite valued case, and again, our results extend this to the countable valued case as long as there's 3 symbols. So over a countable group, that kind of gives us everything, these 2 results together. But this result that I'm mentioning here is actually proven in this more general framework. So for graphs and even for this more general framework of nice permutation groups. Okay. So that's just a bit of history. So what do I actually want to talk about, and what is this mini series about? So that was maybe a long introduction. Maybe it's good for a first talk in the series. But the thing that we're really concerned about are not IID processes by themselves, but factors of IID or finitary factors of IID. And very generally, we want to ask which processes are factors of IID, isomorphic to IID, finitary factors of IID, or finitarily isomorphic to IID. And for this question, let me restrict, when I say process, let me just restrict attention here to Z processes for a moment, or ZD if you wish. Okay, ZD as well. And finite valued, or perhaps countable valued. Okay, but the processes that are at the bottom are always going to be finite or countable valued. On the other hand, when I say IID, factor of IID, in all of these situations, I'm allowing an arbitrary IID. So here, this is exactly the point arbitrary. This is exactly the point where I want to, for example, allow uniform continuous 0, 1. Okay, so that's important for the notion of finitary, but let me not get into that here. Okay, so these are the types of questions we want to ask. And going back all the way to Ornstein already, this machinery of very weak Bernoulli and all of this for the isomorphism theorem, one of the consequences is that being a factor of IID is actually equivalent to being Bernoulli. And it was open and widely believed for a long time that this result, this factor theorem, has a finitary analog. So, finitary factors of IID perhaps are also finitarily isomorphic to IID, but this was recently refuted by Gabor. And actually what he did is he did more than this. He constructed a finitary factor of IID, which not only is not finitarily isomorphic to IID, it doesn't have IID finitary factors of equal entropy or even of entropy just below the process. So there's a gap of where you can't get IID processes as finitary factors. So what this means is that questions 1 and 2 are the same, are one and the same, whereas 3 and 4 are strictly, they're genuinely different questions. And of course, both of them are legitimate questions. But again, being a probabilist, I'm a bit more interested in question 3, which has a bit more probabilistic meaning. So this is the thing I'm going to talk about next. What processes are finitary factors of IID? Okay, so we'd like to characterize these processes. Unfortunately, so far there's no. There isn't really any useful characterization that I know of, at least. On Z, a lot of things are known. So finite state mixing Markov chains are finitary factors of IID, even finitary isomorphic to IID. Countable state Markov chains, which are exponentially ergodic in a proper sense. Finitely dependent processes. And here's another example. I tried to look for some examples. I couldn't find many. That's somehow the point of this. So the TT inverse process, or random walk in random scenery, but with a drift, is a finitary factor of IID. Without a drift, it's known that it's not, in fact. And in higher dimensions, things are even less understood. So here are some results. The plus state of the high temperature or critical Ising model. I'll talk about this a bit more in a minute. So this was shown by Berg and Steif to be a finitary factor of IID. High noise Markov random fields, which is some kind of generalization of high temperature Ising in some sense. A different direction, different generalizations, weak spatial mixing Markov random fields. And we have finitely dependent processes. And then we have some processes which are not Markovian, which aren't Markov random fields. They can have infinite range interactions. For example, like the random cluster model, if you've heard of this before, but which do have a monotonicity property. So in these situations, we know that things are finitary factors of IID. Okay, so this was just to give some examples and just to give you some idea of, what types of things are known. And as I said, I want to focus a bit on this result of the Ising model. This was really as far as I know, the first result about finitary codings in high dimensions, and dimension greater than 1. Okay, perhaps before that, let me add another question. Once we answer this question and we figure out that a process is a finitary factor of IID, a follow-up question is kind of how efficiently can you code the process? You don't just want to write it as a function of IID, but you want to do that somehow efficiently. And there's 2 different types of efficiency that you can ask yourself about. One of them I called here informational efficiency, which is really about using a small IID process. Okay, in what sense? Maybe in the sense first that it's finite valued and not countable valued or not uncountable, as we said before, and maybe even doing it with the low entropy IID process. And then there's a different type of efficiency, which I called here spatial efficiency, which is really about the coding radius. How small can you make the coding radius in terms of, of its tails? Can you make it have finite expectation, maybe exponential moments and things like that. But I'm not going to focus at all on this second one. I'll only talk about informational efficiency here in this talk. Okay, so back to this example of Berg and Steif, and I'm sorry I didn't include a definition of the Ising model. So I hope some of you are familiar with this. It's a very well studied model in statistical physics. Its Gibbs states are Markov random fields, and then they have monotonicity, FKG, and so forth. And there's a Gibbs measure called the plus state, which is kind of the extremal, the largest Gibbs state. And for this Gibbs state, I didn't write it here, but it's known that it's always a factor of IID. Okay, whatever the Ising model has a parameter called the inverse temperature, or temperature. Whatever the temperature is, it's always a factor of IID. But what Berg and Steif showed in this paper is that when you ask yourself about finitary factors of IID, the answer is not always that yes, and it exactly corresponds to the critical point in terms of the statistical physics properties of the model. So at high temperature and criticality, it is a factor of finitary factor of IID, but at low temperature, it's not. And what Berg and Steif showed in this paper is that away from criticality, at high temperature, it's actually a finitary factor of IID in an efficient sense, in an informational efficient sense. You can use a finite valued IID process. And actually, their proof, I'll say maybe one sentence about this. What they do is they run Glauber dynamics for the Ising model in infinite temperature, in infinite volume, like on the entire lattice. And they put this together with ideas of coupling from the past devised by Propp and Wilson, and they showed that that can be applied in the infinite setting exactly to get a finitary factor of IID in the so-called uniqueness regime, so in high temperature or criticality. And really, they worked kind of hard in that paper to upgrade the spatial efficiency that kind of algorithm gives to this informational efficiency of a finite valued IID process. That's kind of what, if you look at their paper, a bulk of it is just to kind of convert the spatial efficiency, which they get, well, for free given what was known about the Ising model into informational efficiency. And they left open this question of what happens at criticality. Can you also do things efficient in terms of the IID process? So at criticality is this plus state of the Ising model, a finitary factor of IID using a finite valued IID process. That's the question that they asked, and this is really what motivated Tom and myself when we started doing this work. And initially, when we started discussions, our ideas were, we started talking about the Ising model. Then we started understanding that the ideas are a bit more general and maybe work for Markov random fields or for things like that. And eventually we ended up with a very general kind of abstract result, more in like the factor theorem of Ornstein and more kind of complementary in Gabor's result. And it doesn't need to know anything about the input process beyond the fact that it is a finitary factor of IID. Okay, and let's say that it has finite entropy. If you wish, you just can think about the finite valued case. And no matter how it was constructed, how inefficiently it was constructed, what this theorem tells you is that you can always do it efficient in terms of the entropy. Okay, so given that X is a finitary factor of IID, for any epsilon, there exists a finite valued IID process of entropy just epsilon more than what you need, such that X is a finitary factor of Y. Okay, so let me just remind you Gabor's result, which says that if X is a finitary factor of IID, it need not be the case that it's finitarily isomorphic to IID. So this is kind of almost, it's complementary. It's telling you that you can almost get there. You can get it as, at least as a finitary factor of something that almost has the same entropy. Okay, and this also has some content when the process has infinite entropy but is countable valued. It says that you can at least use an IID process which is countable valued and not continuous. And actually, we do prove something about finitary isomorphisms. What we actually show is that for any such X, there is a process X prime whose entropy, even whose single site, marginal entropy is less than epsilon, such that the pair XX prime as a process is finitarily isomorphic to IID. Okay, so you can kind of complement your process. You can find a finitarily Bernoulli complement to it somehow. You can add just a bit to it and get it to be finitarily isomorphic to IID. Okay, so this is the result that I wanted to tell you about, and in the time that remains, I can first answer questions, of course, and if there are no questions, I'll tell you a bit about the proof. I'll just open a notepad for that.
So just a naive question, like I'm assuming X prime is not necessarily independent of X.
That's right. It's not necessarily. We don't know it with independent, and with Gabor's result, what you definitely can't hope for is that X prime is independent and IID, because
right.
that would yes, that would contradict his result. But yeah, we don't know too much about this X prime. It's definitely not independent of X. I'll get to that in a moment in the proof, I hope. Yeah. Okay, so this is the result I'd like to tell you a bit about. Okay, so for the proof ideas, let me just talk about Z. That's really, maybe I'll say now, actually, maybe let me get rid of the ZD case. Let me get rid of that, get that out of the way now. The ZD case and the more general cases, actually what we do is we reduce them to a version of Z, a version of the theorem of Z, which is essentially the same, but it's a relative version. It's relative to a process. It's the same theorem, just relative to a process. And then when you have a ZD process or something like that, all you really need to do, and this is kind of, these types of ideas, I guess, are somewhat known. What you need to do is when you have a ZD process, be able to somehow extract from it a Z-type total order, and then you can map that process to Z. And if you have a relative version of the theorems for Z processes, then you can apply that there and then pull it back to the ZD case and things like that. So okay, I won't talk about that. That's perhaps somewhat standard. Maybe some of you know these types of methods. So I'll just focus on the result for Z. And I'll also just talk about finite valued processes. That's also not just to make things technically simpler. Okay, so let me assume that xn is, so we have this process x, and let's assume that xn takes values in a set A, which is finite. Okay, so the very high level idea of the proof is to do the following thing. We want to write x, our process x, as a limit, t goes to infinity, of processes, which I call xt here, where xt are partial processes. I'll say what this is in a minute. Partial processes of x, which increase to x in a proper sense. So what do I mean by partial? I just mean that the values that they take belong to A or some new symbol, which I'll call star, which is kind of undefined. Okay, this limit is actually an increasing limit in the sense that x and t, the only thing I'm allowing is that it equals star, 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 star. It's undefined for some time. At some time, once it gets a value in A, it never changes. Okay, so that's what I mean by this kind of increasing limit. So in other words, these xt's you can think about as, at time t, we have a process which is just a partial process of x in the sense that we revealed some of the values of x and some of them we still haven't revealed, and they're just stars. And then we reveal more and more and more, and eventually we get the entire process. Okay, so we want to write it in this form for some choice of partial processes. And then what we'd like to do is finitarily code each step along the way. Okay, so when we go from xt to xt plus 1, we're revealing some of the pieces of some of the sites, and we'd like to be able to describe the values that additional process that we're revealing as a finitary factor of IID. Okay, and then we can put these together and get the whole process x as a finitary factor of IID, and we want to do this efficiently at every step so that we end up with something that didn't that wasn't too wasteful. Okay, so that's like at a very high level, that's the idea. Let me also say that, if we call, say, x bar the process, which is at every point, it's the sequence. Okay, so this is a sequence kind of belonging to A union star to the n, but it's not an arbitrary sequence. It actually belongs to a discrete subset. As I said, the only sequences which are allowed are ones which are star and then some point, some value in A which repeats itself. This process is very easily seen to be finitarily isomorphic to x comma t, where t is the process where at any point n, it's the minimal t such that xtn is not star. Right. So all I'm saying here is that this entire sequence of partial processes, really all you can have in mind, all I'm saying is that it's the process x together with another process of the times where each site is revealed. That's all I'm saying in this entire first step. Okay, I'd like to reveal the different values at certain times. Okay, so that's, as I said, high level. Let me tell you. Okay, let me give you an attempt at a proof. Okay, following this high level thing, and we'll see why this doesn't work. So this, I mean, this is somehow the maybe the first thing you would think of. Okay, it's really one of the first things that comes to mind, at least given this high level proof, which is also something that is not too complicated, right? So here's an attempt. Let's define xt. Okay, so this is the only choice we can do. Either define it to be xn or star because it's a partial process. And we only have to say when is it xn and when is it still undefined. Okay, and the natural thing to do, remember that what are we assuming? We're assuming that x is a process which is given to us, which we already know is a finitary factor of IID. So we know that there's some IID process and some finitary map from that IID process text. So using that information, I'd like to say, let's let it be xn if the coding radius for that that given for in the finitary coding that we're given at the point n is less or equal than t, and otherwise star. In other words, at time t, we reveal the things that we can figure out, the outputs we can figure out just by looking at a window of size t in the IID process. Okay, that's pretty natural. We reveal more and more because we see more and more. It's finitary, so at some point we'll reveal everything. So definitely point one, you know, the fact that these partial processes increase x, that's definitely okay, because it's we have a finitary factor. So Rn is almost truly finite. At some point, t will be larger, and then we'll reveal the value. Okay. However, the second point, this is what I'd like to explain now. Using this naive type of attempt, in the second point, we're going to run into trouble. We might run into trouble. It might be the situation that, you know, we x1 maybe is very nice and we can finitarily code it using an IID process, but then maybe x2 given x1, you know, the added information maybe is not, maybe is already kind of we might already be in a problematic situation. Okay, so here's the difficulty, just by an example. Okay, so consider the following example. Let's let Yn be IID Bernoulli half, and let's take as our x process the process defined by two if Yn equals Yn plus 1 and Yn plus 2 otherwise. Okay, so it's a very, very simple function of y. It's actually a block factor of y. Okay, so definitely it's a finitary factor of IID. Okay, but this is just an example to explain why this attempt is too naive, why it can't work. Okay. So what can we say about in this example, x1, using this definition here, what is this process? It's just the process of, you know, it either equals xn if the coding radius is less than 1, less or equal than 1. Okay, how do I get another color here? So note that the coding radius in this case equals 1, and in this case equals 2. Right? If Yn happens to equal Yn plus 1, then just by looking at distance 1, we know that the output is 2. But if that's not the case, we need to go one step further because we need to expose the value of Yn plus 2. So the coding radius is either 1 or 2 according to these two situations. So that means that y1, you know, by the definition that we wrote at the top, it's 2 if Yn equals Yn plus 1, and it's star otherwise, because we decided not to reveal the values where the coding radius is 2. Okay, and x2, it's going to be the same thing except that the star is going to be Yn plus 2, and this is very easily seen to be finitarily isomorphic to x itself, right? Because if you know all the locations where Yn equals Yn plus 1, and you also know in some of the places the value of Yn or Yn plus 2, that doesn't really matter, you can reconstruct everything very nicely. Okay, so what x2 is sorry, not x, what well, yes, x and y. I mean, they're both finitarily isomorphic to each other. Right. I mean, definitely, if you know x, you know y, right? Because you know the places where y is equal, and you know some more information. Yeah. Okay. So that means that this whole increasing sequence, I mean, there's just two sequences, x1 and then x2 is already the end. Now, x1 is definitely a nice process. It's a block factor of IID, so there's not going to be any trouble coding it as a finitary factor of IID. But this whole example, what I want to explain is that x2 given x1 is not a nice process. Okay, so what can we say about x2 given x1? Well, x2 given x1, as we said, x2 is essentially the same process as y. And what is x1? x1 is, it's almost the same process as y, but it's missing one global bit. I mean, actually this x1 is also IID Bernoulli half, because if you take IID Bernoulli halves and you keep the places where they're equal, you write that symbol as 2 and that other as star, it's IID half. But given x1, x2 has 2 global possibilities, right? There's 2 ways to recover x2. Okay, so this thing is not mixing. I mean, more specifically, x2 is a 2-to-1 extension of x1. Okay, given x1, there's 2 ways to reconstruct x2, which have equal probability. Okay, so that shows that, you know, in this naive type of thing, you might run into actual problems. I mean, you might at some step not be able to carry out the second step of finitarily coding each step. So we need to do step 1 in a more sophisticated way so that step 2 will be possible to do. Okay, and I don't have much time. I'll just maybe give you the definition that's relevant here, and I won't give any proofs or anything, but maybe this definition already tells you something about what's going on. So perhaps everyone is familiar with the notion of finitely dependent. If not, I'll kind of define it along the way, but really what I want to do is define a relative version of finitely dependent. I want to be in a situation where I want to prove that I can choose these xt's so that xt is nice relative to the previous x's. And the notion of nice that I want to use is relatively finitely dependent. Okay, so that's the notion I'm defining here. Okay, so let's say that x is relatively finitely, or we called it finitarily dependent, or finitely dependent relative to some process w. Okay, if there exists a process k, which is a finitary factor of w, it takes values in n. Okay, such that whenever you have 2 sets A and B in Z, which are, okay, so what is K dependent without the relative notion? I would write if the distance between every element in A and every element in B is at least some number K, then I'd like that X restricted to A and X restricted to B are independent. That's the notion of K dependent, the regular, the standard notion. So in this relative notion, what I'd like is that any 2 sets, now they might be random, but they need to be measurable with respect to W. And here, instead of asking that the distances between A and B are just greater than some fixed number, now I'm going to use this process. And I'll write the maximum between Ka and Kb. And instead of independent, now they're conditionally independent. And all of this should happen almost surely given W. Okay. So relative to W, in other words, conditionally on W, I have some numbers at every site, some Ks, which tell me that, you know, what the distance of the dependency is. And once I get far enough from that distance, things become conditionally independent. So that's the notion of finitely dependent. And maybe very briefly, I'll just say the correction to this attempt, what we want to do is if we think about Z, the problem with this is that every site, even though its window maybe is only of size 10 or something, the windows might together propagate, and they might propagate dependencies very far, as we saw in the example. So what we want to do is just place cut points. And we want to say that if a window, even if it's small, if it intersects this, then we don't reveal the value of the process there. So the only times we reveal things are if Rn is less or equal than T, let's say, but also the coding window, Xn minus Rn, Xn plus Rn, doesn't intersect one of these cut points. And that makes sure that segments that are separated by cut points remain conditionally independent. And then eventually what we do is we prove a theorem analogous to Smordinsky's theorem for k-dependent processes. We prove a relative theorem which says that if you have two processes which are finitarily dependent relative to a common process W, and those two processes have the same conditional entropies, then they're finitarily isomorphic relative to W. And that's what allows us to carry out this second step here. At every step, we know that we're in a situation that things are nice and actually finitarily isomorphic to IID, and therefore we don't even lose entropy. And the only loss of entropy, the only reason we need this epsilon is to create these cut points at the beginning, which we do using a very sparse, low entropy IID process. Okay, so I hope that conveys some of the ideas behind the proof. So I'll stop here. Thanks.
Thank you, Yinon, for a great talk. Are there any questions?
Well, can I ask? So what's so this is? Does your theorem hold for in the more general amenable case? Or is it?
Yeah. Yes. So the scenario here, the setting where this theorem works is in this framework with the added assumption of amenability.
Okay. Yeah.
I mean, we use the amenability, but if you look at the theorem, it makes sense that it's also true without amenability, because without amenability, entropy shouldn't really play any role, but we don't know. Yeah, so it works in the setting of countable groups, amenable groups.
Sorry, could you repeat that?
So the last sentence I said?
Yeah.
Yeah, so it works in the setting of countable amenable groups, or transitive amenable graph, with a small caveat. There's this issue of IID processes needing to be aperiodic. It's a funny thing, but okay, here I'll just draw a picture, and you can think about this. This graph, the theorems don't work there. They're actually not. Yeah, I think they're just not true. Here, so in this graph, it's not true that any two IID processes of equal entropy are isomorphic, even without finitary. There's an added invariant that you have to preserve. So, yeah, but apart from this, it pretty much works on all transitive amenable graphs.
So I think in your paper you mentioned it would work like on the tree or the free group on two generators. If I'm remembering correctly.
Well, I did mention something. That's right, but it's not this theorem. Okay. This theorem needs amenability. We have some results in the paper that would also work for the tree, and that's these about IID processes. So this result that would work on a tree as well. That doesn't need amenability.
Okay.
Yeah. And maybe I'll, just to say something about this general framework, but in a very simple setting, just to give you an idea of what could be the problems. Even on Z, once you introduce reflections into the game, so if you think about it as not as a group, but as a graph, and you look at all the automorphism group, which just means translations plus reflections, it's not obvious anymore, you know, how to, and things change. Things change, and in particular, here's an open problem, which, you know, perhaps I have a solution for this case, but just to have some ideas in mind about these weird things that become complicated with reflections, show that an IID process with two symbols. So say that this IID process is finitarily isomorphic to some IID process with three symbols. Because if you think about what Keen and Smardinsky did, the reduction is it used the direction. It kind of used patterns of the type 1, 0, 0, 0. And if you try to make a pattern which is symmetric, which is reflection variant, the reduction doesn't work.
Okay.
Yeah. So this three symbol thing, it seemed to us that, you know, the methods of Seward can't easily be adapted to this general framework. But, you know, maybe one of you can do that.
Yeah, just wanted to say thanks for the you know, that your presentation of the Mishalkin isomorphism was really nice. But,
yeah, I got some input on that, which helped me from Benji Weiss.
If there aren't any other questions, then let's thank Yinon again.
Yeah, so I don't know what to say, but thanks for the talk. It was
Yeah.
very, very nice. Maybe I'll think of something more to say or ask later on.
Sure. Yeah. Very good.
Yeah, I've been enjoying looking at your paper. That the result that extends, like what you were just talking about, the isomorphism stuff, is a nice result.
Yeah, so I mean, I guess the general thing is that you're generalizing all of the Ornstein-Weiss machinery and Touvenot machinery to finitary to the finitary setting. I mean, I guess some of that was already done by Smardinsky, but it seems like you've got a more general.
When you're talking about Smardinsky, are you referring to the K-dependent paper?
Yeah, I guess so. Yeah.
Yeah. Right. So yeah. So a big bulk of the result is this relative Smardinsky result. Right. Yeah.
Yeah. Probably. Sorry.
I just wanted to say I was happy that. And this is I guess Tom, knowing a lot of ergodic theory, observed this, that we can do most of the things for Z processes if we prove a slightly more general version of a relative version. You can in a previous paper that I did about like finitary stuff on ZD, I just did everything on ZD, and it just makes things more cumbersome. It's nice that things can be decoupled. You just prove something a bit stronger in Z, and then you just reduce everything to Z.
So it's this Rudolf Weiss machinery that you're using to keep, you know, that I'm just want to make sure, right, that entropy relative to the, or you're looking at an orbit equivalence, and then entropy relative to the orbit change sigma algebra.
Yeah, so again, I said at the beginning, I don't know much ergodic theory, but
Oh, I see.
Tom has said a lot of times that this has to do with orbit equivalence, and he keeps telling me that it's about Rocklin's lemma and stuff like that. These the cell process thing that I was describing. Yeah, so it's kind of a finitary versions of these things. Yeah.
Yeah, very nice. Thanks.
Yeah, sure.
Thank you.
Hey, Peter. Peter.